The research proposes an RRAM-Based bio-inspired circuit system for correlation feature extraction and seizure prediction. Inspired by neuronal mechanisms, the system utilizes RRAM to reduce computational energy consumption of seizure prediction algorithms. It achieves a high average sensitivity of 91.2% and a low false positive rate per hour (FPR)H of 0.11 on the CHB-MIT seizure dataset. The system's power consumption is recorded at 24.4 mW during the feature extraction phase and 19.01 mW in the seizure prediction phase, with a cumulative energy consumption of 1.515 microjoules for a 3-second window data processing, predicting 29.2 minutes ahead. This method exhibits an 81.3% reduction in computational energy relative to the most efficient existing seizure prediction approaches, establishing a new benchmark for energy efficiency. The system's operational logic includes unique EEG signal encoding methods, chip architecture reuse strategies, and DA-class-AND network hardware mapping rules. The research also discusses the application of memristors in analyzing epilepsy data, highlighting the use of RRAM for data correlation analysis and seizure prediction tasks. The research proposes an RRAM-Based bio-inspired circuits for mobile epileptic correlation extraction and seizure prediction. It utilizes the CHB-MIT dataset, focusing on 13 patients with at least 2 seizures and 3 hours of interictal period. The EEG signals are filtered to a frequency range of 050 Hz and segmented into 3-second windows. The signals are then encoded into continuous pulse signals to preserve information. The encoded signals are fed into the memristor circuit, and correlation features are extracted based on the overlap in pulse signals. The extracted features are used for seizure prediction, employing a 12-layer neural network. The first layer is directly implemented on the EEG extracting circuits, while the second layer is mapped onto the RRAM chip. The system's energy consumption is discussed, comparing favorably with other studies. The approach leverages the properties of RRAM to mimic biological synapses, enabling efficient and accurate seizure prediction. The research proposes a novel chip architecture and operational logic based on RRAM for reducing power consumption in correlation feature extraction and seizure prediction algorithms. The system achieves a high average sensitivity of 91.2% and a low false positive rate per hour (FPR)H of 0.11 on the CHB-MIT seizure dataset. The total energy consumption for extracting correlation features and predicting seizures is approximately 1.515 microjoules, which is about 81.3% lower than the current lowest energy consumption for seizure prediction tasks. This establishes a new benchmark for the lowest energy consumption. The methodology can be extended to other EEG-related tasks, leveraging the classic characteristics of non-volatile RRAM, such as long-term potentiation, LTP, and threshold effects. This could facilitate the development of low-power chips designed for EEG correlation feature extraction and seizure prediction. Here is a combined summary of pages 7 and 8 of the research paper. This paper reviews various works on mobile epileptic correlation extraction and seizure prediction using RRAM-Based bio-inspired circuits. The authors provide a comprehensive overview of existing literature on seizure detection and prediction using machine learning classifiers, highlighting the importance of non-invasive mobile EEG as a tool for seizure monitoring and management. The authors cite several studies that have employed machine learning algorithms, including convolutional neural networks, support vector machines, and recursive memory brain state classifiers, to detect and predict seizures from EEG signals. These studies have demonstrated high accuracy and efficiency in seizure prediction, with some achieving real-time seizure control using closed-loop neural prosthetic systems. The paper also discusses the potential of memristor-based systems for efficient multiply-accumulate operations and synaptic behaviors, citing works that have implemented fully integrated reprogrammable memristor CMOS systems and fully hardware-implemented memristor convolutional neural networks. Furthermore, the authors highlight the importance of edge learning using fully integrated neuro-inspired memristor chips, which have been shown to achieve high accuracy and efficiency in seizure prediction. They also mention the development of open-source simulation frameworks for resistive deep learning systems, such as MEMTORCH. The paper concludes by emphasizing the need for efficient and accurate seizure prediction systems that can be integrated into mobile devices, enabling real-time seizure control and improving the quality of life for patients with epilepsy.